Capacitors in series. Two capacitors are said to be in series if they are connected end to end such that charge stored in them is same. Consider two capacitors of capacitances C1 and C2 connected across a battery such that V1 and V2 are the potential differences across them. These two are two capacitors in series connected across this battery. Charge on each plate is Q, plus Q, minus Q, plus Q, minus Q. This is positive, therefore this plate takes positive charge. Other takes negative, positive, negative. Potential difference across first capacitor is V1. Potential difference across second capacitor is V2. Let us write like this. So potential difference across first and second. In series combination, charge in each capacitor is same and V1 plus V2 equal to V applied. V equal to V1 plus V2. But Q equal to CV or V equal to Q by C implies V1 means potential difference across first capacitor is Q by C1 and V2 equal to Q by C2. Let us substitute these two in this equation. Therefore, V equal to V1 is Q by C1, Q by C1 plus Q by C2. Let us take Q common factor, Q, remaining is 1 by C1 plus 1 by C2. Therefore, V is Q into 1 by C1 plus 1 by C2. Let this be equation 1. The capacitors are replaced by a single capacitor called the equivalent capacitor. For the equivalent capacitor, suppose this is the equivalent capacitor which when connected across the same battery should store the same charge. So this is plus Q, this is minus Q, potential difference is V. So this capacitor CS stands for series equivalent of capacitors. For the equivalent capacitor, V equal to Q by CS. This is equation 2. So from equation 1 and equation 2, equation 1 is Q into 1 by C1 plus 1 by C2, isn't it? And equation 2 is Q by CS, or CS equal to one by CS equal to 1 by C1 plus 1 by C2, or CS equal to C1 C2 by C1 plus C2. Take LCM, simplify. CS equal to C1 C2 by C1 plus C2. In general, 1 by CS equal to 1 by C1, 1 by C2, etc. plus 1 by Cn. This is for n capacitors connected in series. Capacitors in parallel. Two capacitors are said to be in parallel if they are connected across two common nodes such that potential difference across them is same. Consider two capacitors of capacitances C1 and C2. Connected in parallel across a battery such that Q1 and Q2 be the charges in them. These two are two capacitors in parallel connected across this battery. These two are the nodes. Node means it is a point in the circuit where two or more conductors meet. This is C1, capacitance of second capacitor C2, charge on this plate plus Q1, charge on the other plate is minus, it is Q1, in this case plus Q2 and minus Q2. Since these two are in parallel connected across this, if V is the potential difference, here also V is the potential difference. V is potential difference across the capacitors. In parallel combination, potential difference is same and sum of these two charges Q1 plus Q2 is the total charge. In parallel combination, potential difference across each capacitor is same and that is equal to V, and Q equal to Q1 plus Q2. Sum of these two charges is the total charge, but Q equal to CV implies I want Q1, therefore Q1 equal to C1V and Q2 is C2V. Therefore total charge becomes C1V plus C2V. V is common factor, C1 plus C2. This is total charge Q. Equation 1. Now the capacitors are replaced by a single capacitor called the equivalent capacitor. The capacitors are replaced by a single capacitor called the equivalent capacitor. For the equivalent capacitor, Q equal to C parallel into V. This is equation 2. Cp is parallel combination. So if this is the equivalent capacitor, single capacitor, which when connected across the same battery should store same charge. That same charge is Q1 plus Q2. Okay. So from 1 and 2, CPV equal to V into C1 plus C2, or CP equal to C1 plus C2. In general, for n capacitors in parallel, Cp equal to C1 plus C2 plus C3 plus Cn. Series equivalent of number of capacitors is always smaller than the smallest capacitor. Meaning of this, if this is first capacitor, second capacitor, third capacitor, and this is 6 nanofarad, this is 3 nanofarad, and this is 2 nanofarad. If you find the series equivalent of these three capacitors, it turns out to be 1 nanofarad. You will understand how we got 1 nanofarad. And observe, this 1 nanofarad is smaller than the smallest of these three values. So among these three, 2 nanofarad is the least, and even this is smaller than the smallest. That is the meaning of this first note. For three capacitors in series, one by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3, or Cs equal to C1 C2 C3 C1 C2 plus C2 C3 plus C1 C3. So this is how you should use if three capacitors are given. You can use this formula or directly use this. And which is the common mistake means, when we solve this, we think that Cs is C1 C2 C3 by C1 plus C2 plus C3. So this is the common mistake. This is not the answer. This is not the required equation. That is the second note. If two identical capacitors are in series, then series equivalent is C by 2. Meaning of C by 2, if this is first capacitor, second capacitor, each equal to 3 nanofarad, identical capacitors, then Cs equal to 3 nanofarad, capacitance of each divided by 2, that is 1.5 nanofarad. Extending this argument, we can write, for n identical capacitors, series equivalent is C by n. First capacitor, second, third, fourth, this is 2 nanofarad, 2 nanofarad, 2 nanofarad and 2 nanofarad each. Then series equivalent of these four capacitors is Cs equal to C by 4. C is 2 nanofarad by 4 equal to 2 by 4 is 0.5 nanofarad. So this is how you can use this formula. If there are n identical capacitors in parallel, then Cp, parallel equivalent of n identical capacitors, it is n times C. This is first, second, third, fourth. If these four capacitors are in parallel, let each equal to 1 nanofarad. 1 nanofarad. Identical values, identical capacitors in parallel means Cp equal to, there are 4 times each equal to 1 nanofarad equal to 4 nanofarad. So this is how we can use. In the next video, let us see different combinations of capacitors and how to find equivalent capacitor. Energy stored in a capacitor. This is a capacitor connected across a battery. This is positive terminal and negative terminal. Let V be the potential difference across the capacitor. Because of this positive potential of the battery, electrons are withdrawn from this plate. Because this positive can attract electrons, conduction electrons present in this plate. And those conduction electrons are transferred to the other plate. Since electrons are removed from this plate, it takes positive charge, and electrons are transferred to second plate means it takes negative charge. Observe, because of transfer of charge, because of transfer of electrons, charge is developed on both the plates of a capacitor, and that's because of this battery. The battery is pumping electrons from one plate to another plate. This is similar to pumping of water from ground level tank to overhead tank. If this is a house, this is tank. If this is water, then job of the pump is to lift water like this. Similarly, the battery is pumping electrons from one plate to another plate. Here, work done by the pump is stored in water as potential energy. In this case, work done by the battery in pumping the electrons is stored as energy, and that is the stored energy in capacitor. In first step, let us find out work done to transfer small charge. So it is V into dq, because V is constant. V is the applied potential difference. So what is the work done by the battery to transfer small amount of charge means this. To find out total work done, we have to integrate this equation. And this work done is the potential energy, because it is a conservative force. As a result, this work done is stored in the form of potential energy. And to solve this, let us use Q equal to CV equation. Okay. Using these two steps and this equation, we can get the final expression. Consider a capacitor of capacitance C connected across a battery such that V is the potential difference across it. Positive terminal of the battery transfer electrons from one plate to the other. positive terminal of the battery transfer electrons from one plate to another. The work done to transfer small charge dq from one plate to another plate is dW equal to potential difference into charge. So dq is the small charge transferred. As a result, dW is the small work done. Work done to charge the capacitor by charge q is total work done equal to integration of work done equal to integration of V into dq. Limits of integration are from 0 to 0 means uncharged capacitor to charge q. Q equal to CV or V equal to Q by C. Therefore, work done equal to integration. In place of V, we can write Q by C into dq. Limits are from 0 to Q equal to 1 by C is constant. Take this outside. Integration of Q into dq from 0 to Q equal to integration of x to the power of n into dx is x to the power of n plus 1 by n plus 1. Increase the exponent by 1, write the same exponent in the denominator. Therefore, in this case, q integration of q is q square by 2. So after integration, write limits like this 0 to q. It is q to the power of 1. 1 plus 1 is 2. That same exponent is in the denominator. Now substitute upper limit to this 2c 1 by 2c. Substitute upper limit q square minus substitute lower limit 0, which is equal to q square by 2c. This work done is stored in the capacitor called potential energy. Stored energy is called potential energy, isn't it? Therefore, potential energy equal to half q square by c. Let us denote potential energy by U bracket. Now, different forms of potential energy. This is expression for potential energy in terms of charge and capacitance. Half q square by c, but q equal to cv implies potential energy equal to half, in place of q write cv, therefore cv its square whole square by c equal to c square v square by 2c. Or potential energy equal to half c v square. This is the expression for potential energy in terms of capacitance and potential difference. Also, in this step we have substituted for q. Now let us substitute for c. Also, c equal to q by v implies potential energy equal to q by v in this expression half q square by q by v. Q get cancels, so it is half into q, this v goes to numerator, v. So this is the expression for potential energy in terms of q and v. Therefore potential energy in terms of q and v, half q v. In terms of cv, half c v square. The last combination in terms of q and c, half q square by c. If sigma is surface charge density, then sigma is q by a, or q equal to sigma a. Second expression, capacitance of parallel plate capacitor. Capacitance of parallel plate capacitor is C equal to epsilon naught A by D. What is A? If there are two plates in a capacitor, parallel plate capacitor, then area of each plate is A, distance between the plates is D. Consider potential energy. We have expression for charge and capacitance. So let me consider potential energy U in terms of Q and C. So it is half Q square by C. Let us substitute Q and C. Q and C, these two expressions in this expression. So we get potential energy equal to half Q square. Q is sigma A its square by C is epsilon naught A by D. Equal to half sigma square by epsilon naught A square by A is A, D goes to numerator, D. So since it is sigma square by epsilon naught, imagine epsilon naught by epsilon naught here. Then the expression turns out to be sigma square, half as usual, sigma square by epsilon naught into epsilon naught is epsilon naught square. Numerator epsilon naught is there, epsilon naught. Area into length gives volume, capital V. So this is the expression for potential energy. We also know that electric field due to a conductor, charged conductor. Electric field at a point due to charged conductor is sigma by epsilon naught. Here we have sigma square by epsilon naught square. Therefore, potential energy equal to half sigma square by epsilon naught square is E square epsilon naught. Let me take this volume to the other side. Divide this by V. So what is left hand side? Potential energy by volume. So we can call it energy density. Therefore, energy density equal to potential energy by volume equal to half epsilon naught E square. This will remind us expression for kinetic energy, isn't it? Half mv square. Similarly, half epsilon naught E square. So this is the expression for energy density. Now, probable questions. Mention an expression for energy stored in a capacitor in terms of capacitance and charge. This is for 1 mark, just the expression in terms of capacitance and charge. Expression for energy in terms of capacitance and potential difference. 1 mark, capacitance and potential difference. Expression for energy in terms of charge and potential difference. Again for 1 mark. Mention an expression for energy stored in a capacitor in terms of energy density in a capacitor. Energy stored in terms of energy density. Energy density is energy by volume. 1 mark. Energy in a capacitor when connected across a battery is E. E is not electric field. E is energy. Okay. It is clearly mentioned. What is the energy if applied voltage is doubled? You have to consider expression for energy in terms of capacitance and potential difference. And based on this, you have to decide. 1 mark. So instead of U, they have mentioned E. E stands for energy. Energy stored in a capacitor when connected across a battery is E. E is energy. What is the energy if capacitance is doubled and potential difference is halved? Capacitance is doubled, potential difference is halved means find out expression for energy E in terms of C and V and apply these two conditions. This can be asked for 1 mark or 2 mark. Similarly, this is for 1 mark or 2 mark. Potential energy of an electric dipole in an external electric field. Consider an electric dipole in an external electric field E. The dipole moment is given by P equal to Q into 2A into P cap, small letter P. Where Q is magnitude of each charge, 2A distance between the charges, P cap is unit vector from minus Q to plus Q along the line joining the charges. We know torque on the dipole. torque on the dipole is tau equal to P cross E vectors, or magnitude of torque is P E sin theta, where theta is angle between the direction of dipole and the direction of electric field. There is no vector symbol. Observe that this is magnitude of torque. Work done by the external torque, tau, let me write EXT. EXT stands for external. Work done by the external torque to rotate the dipole through d theta. dW equal to tau external into d theta. This is similar to work done equal to force into displacement. In the case of rotational motion, it is torque into angular displacement. Therefore, work done to rotate the dipole from theta 1 to theta 2. Work done to rotate the dipole from theta 1 to theta 2 is, so we should find the total work done equal to integration of dW equal to integration of tau external, which is a function of angle external torque. So torque into angular displacement is work done. So integration of small work is total work done. So limits are from theta 1 to theta 2. Actually, diagram is not necessary, but with diagram it is easy to understand. If this is the external electric field, uniform means it should be shown by equidistant parallel lines. So this is external electric field E. This is a dipole. This is minus Q plus Q. Dipole moment is from minus Q to plus Q along the line joining the charges, isn't it? Now this angle is theta 1, angle made by the dipole with respect to electric field. Now the dipole is rotated from theta 1 to theta 2. If this is new position of the dipole, then angle made by this dipole with respect to external electric field is theta 2. This is the meaning total work done equal to integration of torque into d theta. D theta is very small angular displacement. What is the work done to rotate the dipole through small angle d theta means it is dW equal to tau into d theta. So what is the total work done to rotate the dipole from this position to this position means it is integration from theta 1 to theta 2. Okay. Work done P E sin theta d theta, integration, limits are from theta 1 to theta 2. P E constant, integration of sin theta is minus cos theta. P E minus cos theta, limits are from theta 1 to theta 2. Take minus sign outside, minus PE, give upper limit cos theta 2 minus lower limit cos theta 1. So this is the total work done. So this work done is stored in the dipole as potential energy. This work is stored as potential energy of the system. Natural choice of zero potential energy is taken at theta equal to pi by 2. Okay, we will understand that now. Natural choice of zero potential energy is taken at pi by 2. Now let theta 1 be equal to pi by 2 and theta 2 equal to theta. If theta 1 is pi by 2, then cos pi by 2 is 0. If this term is 0, then this theta 2 is replaced by just theta. Potential energy equal to minus P into E minus P into E cos theta because theta 2 is theta minus cos pi by 2 minus PE cos theta. Left hand side is a scalar quantity, potential energy, but right hand side with two vectors and angle between the vectors along with cos theta means this potential energy can be written as minus P dot E. So dot product of dipole moment and electric field along with negative sign is potential energy. And what is the meaning of theta 1 equal to pi by 2, 0 potential energy, and theta 2 equal to theta means if this is external electric field, this is the position of the dipole, okay, minus q to plus q. So at this position of the dipole, potential energy is taken as 0. Potential energy, we are using the symbol U, okay, it is just a symbol. So potential energy equal to 0. So from here, is it rotated anti-clockwise or clockwise? That matters. So this is electric field. Students, please note, these diagrams are not necessary for this derivation, okay. Now special cases, if theta equal to 0, then cos theta equal to cos 0 equal to 1. This is 1, therefore minus P into E. With negative sign, P into E means this is minimum potential energy. Now second case, if theta equal to pi by 2, then cos pi by 2 equal to 0. Cos pi by 2 is 0 means this is 0, this is 0. So potential energy is 0. So potential energy is 0 if theta is pi by 2. Third case, if theta is pi, cos pi is minus 1, implies potential energy equal to P into E, minus of minus, minus of minus, plus P into A. Observe, this is minimum, this is maximum, and this is 0. Potential energy is maximum. This is a derivation for 3 marks or for 5 marks.